In this video, we will be talking about solubility, and I know you're probably thinking, we've already talked about solubility, why are we talking about it again? So all of the solutions that we're going to deal with are aqueous, right? We're talking about water solutions. So in terms of aqueous solubility, what we have done so far is determined if something is soluble, by which we mean it dissolves in pure water, or it's insoluble, meaning it doesn't dissolve in pure water, and these two things are dictated by the solubility rules. Now that we have learned about equilibrium, we can talk about degrees of solubility. So we will be dealing a little bit with the borderline cases of the slightly soluble, but we will mostly be dealing with the things that we said were insoluble, because there's always just a little bit that goes into solution. So, for example, calcium fluoride is an insoluble salt. However, if you have calcium fluoride in a solution of water, there's a tiny, tiny bit that will go into solution. And then, it will establish an equilibrium because only a little bit of it will go into solution. Some of it will precipitate back out. A little bit more will go into solution. And so the solid is in equilibrium with the same ions that you would expect to see, right? This is an ionic compound. So with calcium 2 plus aqueous and 2F minus. So we could write an equilibrium constant for this, right? It's an equilibrium equation. We could write a KEQ, and we need products over reactants, but our reactant is a solid, so it's not going to show up. So this is just calcium 2 plus, that concentration, times the concentration of F minus squared. And to make things a little more complicated, well, not necessarily complicated, do you remember we had equilibrium constants with concentrations, and we called them Kcs, and with pressures we called it Kp, and when it is a solid that is partially soluble, we call this a Ksp, and this Sp stands for solubility product. So if you are looking at tables of data, say in an appendix, you will find a table of Ksp values, and that's just a bunch of equilibrium constants for insoluble salts. So we will use this Ksp exactly like an equilibrium constant because that's what it is. So the major way that we are going to use this is in calculating something called the molar solubility. So molar solubility is what it sounds like. It is the solubility in molarity, so in moles per liter. And we can calculate this from Ksp. I'm going to underline calculated. It cannot be determined directly from Ksp. And this is for a few reasons. So Ksp, this equilibrium constant, has one temperature-dependent value. This usually means that it was done at 25 degrees Celsius, and this value was determined in a completely pure water solution. The actual solubility depends on other factors. So it will depend on other ions in solution, which will be something called the common ion effect, which is just Le Chatelier back to haunt us, and really similar to what we saw with polyprotic acids. And that, I believe, comes up in the next video. So the molar solubility that we calculate, we're going to do an example right now. The way that it will come up in problems is that you'll be asked to calculate the solubility of a salt. We're going to do silver chloride as our example, and what they're asking you to do is calculate the molar solubility. So again, these Ksp values are in the appendix / equation sheet / these are constants that you can look up, and hopefully, as you would expect, they're very, very tiny, right? We're talking about insoluble salts. So we should expect an equilibrium constant, right, that is small because we don't have a lot of product. The products are the ions dissolved in solution, right? So you see, for example, for silver chloride, it has a Ksp value of 1.77 times 10 to the minus 10. Right, very, very small. So let's calculate the molar solubility for silver chloride. So essentially, this is asking you how much of this really goes into solution. So we're really finding X, which sounds awkward and not very clear. We're really finding the concentration of one of the ions in the solution. So you'll see, right, we have an equilibrium. We better set up a rice table. The finding X will be clear once we get this set up. So let's do our silver chloride rice table. So we're talking about this salt going into solution. So I should get silver 1 plus and Cl minus. Initially, well, don't worry about the solid. And I start out with 0 ions, so my reaction has to move to the right. The change, well, it's nothing for the solid, but it's a plus X for silver and a plus X for chloride. So at equilibrium, I have X and X, right? This is just find out what 1X is equal to, and that's your molar solubility. So, well, I know how to set this up. I have a Ksp value, right? I have an equilibrium constant. I need an equilibrium constant expression, which is X squared, and that's equal to 1.77 times 10 to the minus 10. So I find X, which is equal to 1.33 times 10 to the minus 5th. So this is the molar solubility, right? So I'm going to put my answer in a sentence. The molar solubility of silver chloride is 1.33 times 10 to the minus 5th molar, right? Find X, stick a unit on it, and that is your molar solubility. Let's do one more example just so that we can see how the variation works for different stoichiometries of salts. Let's calculate the solubility of lead chloride. which has a Ksp of 1.17 times 10 to the minus fifth. Well, I need a rice table. My lead chloride dissolving in solution. I get a lead 2 plus and 2 Cl minuses. Nothing in my solid column matters. Initially, I start with 0. When my reaction moves to the right, I will make plus X of the lead and plus 2X of the Cl minus. So at equilibrium, I'm at X and 2X. My equilibrium constant expression is X times 2X squared. Again, as always, make sure that 2 is inside the parentheses or your answer is going to end up very wrong. This is equal to the equilibrium constant. So I'm really working with 4x cubed equals 1.17 times 10 to the minus fifth. So x equals 1.43 times 10 to the minus 2. This is still my molar solubility. So the molar solubility of lead chloride is 1.43 times 10 to the minus 2 molar. All right. So you can also, just like we did with all of our other equilibrium problems, do this in reverse. So you could calculate the Ksp. Now, honestly, in a practical situation, this is more likely because we could do something that measures the concentration experimentally, and then we use those concentrations to figure out what the Ksp is. So, like most things, this is best done with an example. So our example is that the solubility of, make this a little more complicated with an extra step, silver sulfate is 1.4 times 10 to the minus 2. Calculate Ksp, and let's just say that all of this is at the same temperature, which is 25 degrees Celsius. All right, so the solubility is 1.4 times 10 to the minus 2. This is basically, right, if we base it on what we have done before, this is our X value. So we do still need to set up a rice table to find out what the pattern of X's looks like in our equilibrium row, and then we can plug this value in for them and calculate the Ksp. So, rice table. Now I have to figure out what silver sulfate looks like, so this is a good place to make sure that you are fully brushed up on your ions, so Ag2SO4. So this would be in equilibrium with 2 silver plus and an SO4 2 minus. Don't worry about my solid. So if I were to put some of this in solution, it goes to equilibrium. I start out with 0. My change is plus 2x and plus x. So 2x and x. So this looks like my lead situation. So we got 2x, that quantity squared, times x, which is equal to 4x cubed. So to calculate, this would be equal to my Ksp, so 4 times that solubility value, which is 1.4 times 10 to the minus 2, that whole thing cubed, and we get a value of 1.1 times 10 to the minus fifth. This is our Ksp.